Okay, today we are happy to have Kaif Hilman from University of Bonn, and he's gonna tell us equivariant localizing motifs for finite groups. Let's
Right.
welcome.
Yeah. So thanks for the invitation to speak here. So yeah, today I want to tell a bit about this joint thing I'm writing with Maxime Ramsey, and yeah, just as a kind of rundown of what I want to roughly say, I'll give some motivation for what equivariant localizing motifs is about. I will then recap what is the language and technology that I need, which is this equivariant category theory thing. I'll define what I'll mean by equivalent localizing motifs, state the theorem, and uh, yeah, the main part of talk that I want to focus on is like the sketch of the proof for sort of like the non-trivial statement somehow, and then I'll give two applications of this. Okay, so yeah, so what are localizing motifs? I'm not going to assume that people have seen much of algebraic K theory, so let me just quickly recall it here. Right, so the non-connective algebraic K theory functor factors universally through this category called mod log or localizing motifs. This was constructed by Blumberg, Gepner, Taboada. People didn't quite know what to do about this thing other than a convenient organizing language. Um, Nonetheless, this was an important result because this was, up until now, this was the only proof that K theory is a leg-symmetric monoidal functor. So for structural purposes, it is very important result because the way you show it is that you say that U is a symmetric monoidal functor, and then you say that mapping out of the tensor unit is of course leg-symmetric monoidal, and so this whole functor is leg-symmetric monoidal. So yeah, actually in a separate work in progress with some other people, I have a new proof that K theory is leg symmetric monoidal that doesn't go through motifs, but let's just say up until today, this is kind of like the only known proof. So this result is very important for this, just for this reason alone. Anyway, there have been many like recent breakthroughs on this modlog guy. One of them is this series of work by Sasha Efimov, um, who showed a lot of very difficult things about modlog, but nonetheless, it says that kind of, while this is a very crazy category, it is nonetheless, understandable from many aspects. So this is one of the big kind of recent developments in the subject, but I'm not going to focus on that for today's talk. Today, I want to rather focus on this recent result by Ramsey Sosnovingas, who showed that surprisingly, modlog is a Dwyer-Kahn localization of cat-perf. By the way, I should say cat-perf for me means small stable categories which are idempotent complete. So like compact spectra and perfect complexes and so on. Anyway, um, so the traditional construction by Blumberg, Gepner, Taboada constructed modlog by saying that okay, I can take presheaves on cat-perf, up to set theoretic issues which I don't want to talk about. More or less, you just take presheaves on cat-perf, and then you take some Balsville local subcategory, and that's what motifs is. But surprisingly, it turns out you don't have to pass the presheaves and you can just invert a bunch of arrows in here. This is, I mean, if you've never done this subject, this sounds kind of random, but this is actually very important because it allows us to talk about nonlinear operations on mod log. So from Blumberg, Gepner, Taboada's construction, you only know how to map out of mod log. You only know how to construct co-limit preserving maps out of mod log. Essentially because of because of how presentable categories work. The category PRL. The category PRL has the word L in it, which means co-limit preserving functor. So you only know how to map out of mod log using co-limit preserving functors. But this fact that you can construct this as a Dwyer-Khan localization actually allows you to consider a lot of other endo functors on mod log, for example, which are non-linear, which are not co-limit preserving. So for example, you can study power operations on K-theory using this sort of fact that you can construct it via Dwyer-Khan localization. So this is very important, and this is going to be somehow like the main theme of the talk today. Um, Another fun thing you can get out of this is that um, you can deduce, because Dwyer-Khan localizations are always essentially surjective, that this map U is actually essentially surjective, which says that every motive is actually the motive of some stable category. This was just not known before at all. And this is kind of surprising actually. And from this, you can actually deduce that actually every spectrum is the K theory of some stable category. This was also kind of not known from before. So yeah, these are kind of very surprising and deep results. And yeah, somehow this project takes this as a starting point. And now I want to introduce the word equivariant. So let G be a finite group. Um, yeah, so right. So what is CatPerf? CatPerf is the category of small stable categories which are idempotent complete. So yeah, as I said, the examples are like complex spectra and so on. Does that answer your question? Okay. Yes. Sorry. So yeah, let G be a finite group. Here are a bunch of questions that you can ask if you're an equivariant person. You can ask yourself, what should equivariant K theory be? And this is an old question that's been studied by like many people. So here's like an example list of them. Um, More pertinent to us is what equivariant localizing motifs should be. And this is the purpose of this talk. Yeah, so I kind of explained a bit just now that K theory is a Lex symmetric monoidal functor because, by this motivic construction. You can ask yourself if equivariant K theory is G Lex symmetric monoidal. I'm not assuming that people know what these words mean, but we'll review them later. But sort of essentially, the question is whether or not K theory admits equivariant power operations. Another question, just based on what I told you just now, is you can ask, is every genuine G spectrum the equivariant K theory of some G stable category, whatever that means. So these are sort of a bunch of questions that you could ask and that you might have asked before. Here's another question that you can ask, isn't G motifs done? Um, the answer is kind of yes, but not really. And here I want to explain to you why some obvious guesses are not really the correct thing. So you can ask yourself, if you can just use this functor, meaning to say, you have the motifs functor from catperf to modlog. I just hit it with fun BG both sides. This takes category with a G action, produces for me a motif with a G action. Seems pretty good. The problem is this is somehow it doesn't have the right universal property because this kind of thing is only universal for invariants which come from something like this. So, suppose I have a functor E, I can also apply fun BG from catperf to fun BG comma E. And then you're going to kind of admit a unique map from this modlog from the universal property. But there are many invariants which don't look like this. For example, this type of thing, right? I can take a category with a G action. I can take homotopy fixed points, and then I take K theory that produces for me a spectrum. And this is not the kind of thing that uh, this this version of U can see. And this is of course very important because this is more or less something about K theory of representations. So in some sense, this was already like a bad idea from the get-go. Here's another thing that you can do. If you know some more equivariant things, you can say, oh, let's take Mackey functors instead. So Mackey functors is roughly, the datum of a stable category for every subgroup H, with a bunch of maps between them. Like there's restrictions and then transfers and so on. And you can still apply, you can apply Mackey on U and you get this map. Why is this not the correct thing? Well, this is actually not so bad. And this was actually used by Clausen, Matthew, Naumann, and Noel in their proof for one of the ingredients for a chromatic redshift. So, I mean, this is like a useful construction, but nonetheless, it is still not really the correct notion because, I mean, there are many reasons. One of them is that Mackey functors are extra structure. So in general, you can't really do category theory with it. So, things are structures and not categorical properties. But, this is a bit vague and it's a bit hard to explain. But roughly speaking, um, this doesn't have nice categorical properties that you would usually be able to manipulate if you work with PRL or CatPerf or something. A more concrete reason is that this thing does not, or at least it's not known to support any multiplicative norm. So as far as I know, there are no known Hill-Hopkins-Ravenel norm on this category of Mackey functors on CatPerf. So, if I can't talk about norms on this thing, how am I even going to start to talk about norms on K-theory? So this is just, never going to work, or at least not with current knowledge. Anyway, so here are some things that you can try and some reasons why they're probably wrong. And the general approach of the solution, well, wrong is a strong word. There are some reasons why it's not ideal. Um, Here's a general approach of the solution, and the solution is to use the theory of G categories, which we'll review in a moment. But sort of roughly what the talk is going to be about is that once I've defined G categories, I'll tell you what the equivariant version of CatPerf should be, and it turns out that this one does support multiplicative norms. Using this, I can then define mod log G following Ramsey-Sosno-Wingers. And then the meat of the talk is going to be that there is going to be a tricky sort of non-linear phenomena that is kind of a bit tricky to deal with, involving a bunch, equivariant cubes and all this kind of stuff. And then I want to explain what are the techniques you can use to kind of overcome these issues. So that's roughly the shape of the remaining talk. Okay. Yeah, so now I want to review some language of G categories as introduced by Barwick, Dotto, Glassman, Nadine Shah, under this umbrella term of parameterized higher category theory. So as a definition, G category is nothing but an object in cat G, which is defined to be categorical presheaves on OG. So OG is the orbit category of the group G. So the objects are just cosets G mod H, and then maps between them are just equivariant maps. Um, I'm going to always indicate an object in here by this underline notation. So whenever I put an underline, it should remind you that we are viewing something as a G category, so as an object in here. Just to give you a visual idea for what an object in here looks like. So let's say the group is CP, so quite simple. Then the datum of a G category is going to look something like this. So this is what the opposite category for CP looks like. You have the coset CP mod CP, then you have coset CP mod E. That's the CP's worth of automorphism here. And then you have a map this way. Cat is just, the datum of a category at level CP group. And then there's an action by CP here, and then you have this restriction functoriality. So that is sort of roughly what it looks like. But I want to highlight here that, therefore, when I say G category, I don't just mean a category with a G action. I mean like this whole stuff worth of data. Again, like, if you've seen equivariant homotopy theory, then this should not be so surprising because people have realized for the longest time, I don't know, since maybe the 60s, that when you want to study equivariant homotopy theory, you shouldn't study a homotopy type with a G action, but you should rather study what's called genuine G spaces. So these are, presheaves on the orbit category. And the reason is because, let's say, for example, when you study equivariant manifolds, um, just remembering the underlying homotopy type with a G action means that you've forgotten a lot of things. For example, you've forgotten the homotopy types of the actual fixed points. The actual fixed points are things that you cannot recover from homotopy theory. These are somehow extra structure. So people have sort of realized a long time ago that you should really work with pre-sheaves on the orbit category. And now the insight of this parameterized category setup is that you should categorify this insight. And here are some points why you want to do this. So, by doing so, you have internal notions of G adjunctions and G colimits. Right? So, categorical pre-shapes are after all naturally a two category. So you can talk about adjunctions. These are just level-wise adjunctions. And here's important. You can talk about G colimits and G limits with respect to any equivariant category I. So let's say I have a G category I, and I maps uniquely to the point. There's also the internal functor category. So I can take functors out of this thing. And by contravariant functoriality, I get this map I upper star going from C to functors from I to C. And because you have this internal notion of adjunction, you can ask, whether this has a property of admitting left or right adjoint. And the left adjoint is called a G colimit, and the right adjoint is called the G limit. And this is very important, as we'll come to in a bit. Yeah, so the next three notions are introduced by Nadine in his thesis. So you have the notion of a G presentable category. I'm not going to go into too much detail what this actually is, but you can think of it at least as a non-full subcategory of pre-sheaves on OG valued in presentable categories. So roughly a G presentable category is going to be the datum of a bunch of presentable categories for every subgroup. And then you have restriction maps which preserve colimits. And it turns out that being G presentable essentially means that these restrictions admit left adjoints and they have to satisfy some double coset formula. Yeah, so that's that. You have also an internal notion of G stability, which is not the obvious one. Roughly speaking, cat perf G is going to be, again, a non-full subcategory of pre-sheaves on OG valued in cat perf, but I want to kind of specify a bit more what you need. So in particular, this means you are a G category, which level-wise is stable, and the restriction functors are exact, like you preserve finite limits and colimits. But you require more, namely that these restrictions, let's say from level H to level K, admit both left and right adjoints, which I'm going to denote by ind and co-ind. And it turns out that there's a canonical map between these two, and then you require that map to be an equivalence. So, as a slogan is ind equals or co-ind. In classical equivalent homotopy theory, is also called the Wigmore isomorphism. So somehow what Nadine was trying to do was kind of trying to axiomatize what are the essential features of genuine G spectra. So, of course, as a main example is genuine G spectra itself. So you can view this as a G category, which at level H assigns for you the category of genuine H spectra, which, if you've never seen, you can take as a definition just to be H Mackey functors valued in spectra. Yeah, so that kind of this definition is really just trying to axiomatize the important features of this category. And the last thing is that you can talk about G-symmetric monoidality. There's a proper definition for this, but in this specific case, we might as well just view it as such, as the following thing. So a G commutative algebra in categories is nothing but G Mackey functors in categories. So just to unpack this notion a bit, what this means is that you have, for every subgroup, you have the datum of a symmetric monoidal category, and all the restriction functors are symmetric monoidal. And moreover, you have wrong way maps going in the opposite direction of the restrictions. And these are things that you're supposed to view as norms. So, the example of genuine G spectra you have the restriction functor, which is symmetric monoidal from, level G to level H, let's say. And you can norm up a H spectrum to become a G spectrum. That kind of, you can package all of that to make this G spectra to become an object in here. So here, you see, like, you already have a language to be able to talk about norms and so on, kind of in a coherent infinity categorical way. So yeah, here are reasons why this is important. Sorry, what you can do, and here the reasons why it is important. So the first is, as I said, you can talk about norms infinity categorically. This is crucial, the fact that you can take G colimits over genuine G spaces. So, in general, you only know how to take colimits indexed by an ordinary category, but in this world, you can talk about colimits indexed over an equivariant category, in particular an equivariant infinity groupoid or genuine G space. And this is very important. And the second thing is that you're able to talk about these equivariant cubes. So, what are cubes? Cubes are, after all, just, delta 1 to the n. Is this some finite product of delta 1? Um, but you can imagine I can take delta 1 to the finite G set. I take a product index over a finite G set, and so the group G acts on the cube. And this is not a thing that you can capture in ordinary land, and you really need to work in this cat G to be able to kind of encode such an object. And we'll see later why this is important. Right, so on the subject of being able to take equivalent colimits with respect to spaces, now you can do this thing I like to call categorical isotropy separation. So in equivariant land, I would say what the most important technique is isotropy separation. This is the thing that you use to prove any kind of non-formal statement. So here P is like, the family of proper subgroups, and you have this co-fiber sequence in pointed G spaces. And why this is useful is that if I want to study some object, I can smash it with this co-fiber sequence to kind of isolate the different parts. So the part captured by this EP plus are those information about the object that is concentrated in all the proper subgroups. And then this EP twiddle is the part that somehow captures, the information that really just comes from the group G. Why this is useful is that you can now do inductive proofs, right? You can prove somehow by inducting on the size of the group. I take my object, I smash it with this co-fiber sequence. I say that, oh, the part associated to this EP plus is handled kind of by induction on the size of the group. And then that reduces the problem to just dealing with this one last thing. So this one of the key techniques in equivalent homotopy theory. Anyway, this is important, and traditionally this is used to study things like genuine G spaces or G spectra. But now the point is that once you've categorified everything, you can do this to G presentable categories themselves. So PRL G stable just means the category of G presentable G stable categories. So the fact that I can take colimits with respect to these things allows me to perform this isotropy separation at the categorical level. So that's all the review that I want to do about equivalent category theory. So before I go on, let me just see if there are any questions. Okay, yeah. So if they are not, also, like, just feel free to ask at any point of the talk. But yeah, so now with the language set up, I want to introduce like the main definition. So I've already told you the category of G stable categories, that's catperf G. But you can imagine I can actually assemble the various G to make this whole thing into a G category. So I can view catperf underline itself as a G category. What is more, this is in fact a G commutative algebras in G categories, meaning to say this guy has got norms. So, for example, there is a norm functor going from H stable categories to G stable category by kind of equivariantly tensoring up my stable category. So that's something you can do. So yeah, if this makes you uncomfortable, you can kind of think of CatPerf as a non-full subcategory of Mackey functors in CatPerf. I don't know, that's another useful way to think about that. So, recall a Mackey functor is just, you know, a collection of categories for every subgroup, and then you have restrictions, and then you have the transfers. But now this CatPerf sits inside here non-fully as those things for which the transfer has the property of being the left adjoint to the restriction. It might be a bit weird because, here we're talking about property, whereas Mackey functors is extra structure. But the point is that being a Mackey functor in particular means you have a bunch of, double coset formulas. Those double coset formulas transformation from the identity or those transformations to be the adjunction units and co-units. And that's why it's fair to say that this has a property of living in here. Anyway, that's a bit technical. I don't want to get too much into that, but here's in case you're not comfortable with this notion, you can just think of it as an object here. Okay, so a Karubi sequence is a sequence in CatPerf which is fiber-wise a Karubi sequence. So in non-equivariant land, a Karubi sequence in CatPerf is just a fiber-co-fiber sequence in CatPerf. That's a definition. That's the standard definition in K-theory. And now I'm just saying, in this equivariant context, I can check Karubiness just by checking level-wise. Right? After all, a G category is the datum of a bunch of stable categories for every subgroup, and I just ask at all these levels, they are fiber-co-fiber sequences. And this shouldn't scare you because, in fact, Barwick showed that fiber and co-fiber sequences in Mackey functors are kind of computed level-wise. So there's something you can just check. An important sort of property of a Karubi sequence is that this first map here is fully faithful because that's how fiber sequences work in categories. But yeah, this point will come up again in a bit. But so that's a Karubi sequence. And this is what a G localizing invariant is. So there's a lot of words. Let me just say them out loud and I'll tell you how to think about this if you've never seen them before. Suppose I have a G stable category. Actually, it doesn't need to be presentable. Yeah, if I have a G stable category E, and suppose I'm given a functor from straight E from catperf to curly E, we say that this is a G localizing invariant if it preserves filtered colimits. It sends Karubi sequences to co-fiber sequences here, and furthermore, it takes this co-induction, it preserves these co-inductions. Okay, let me just unpack this. Non-equivalently, what this is, by the way, yeah, if you've seen a non-equivalent definition, then you don't have to stipulate this last property of preserving co-induction. It turns out that sending Karubi sequences to co-fiber sequences already guarantees that you preserve direct sums. But it turns out in the equivariant land, this is not enough to guarantee that you preserve equivariant direct sums. That's how you should think about co-induction. These are somehow, yeah, you take direct sums, but remember that you are summing over a finite G set, so there's G actions. So this is not something you can capture with a Karubi sequence, so you have to further require this. Anyway, the intuition for this non-equivalently is that somehow localizing invariants are like homology theories on stable categories, right? Homology theory, if you remember this, whatever the Eilenberg-Steenrod axiom says that, you are an invariant, and the key property is that it satisfies the Maya-Vittori's principle, which says that, if I have a push-out square, then, when I apply my invariant, this gives me a long Z sequence or whatever. This, localizing invariants are just supposed to capture this, but for stable categories. important examples of localizing invariants are things like, K-theory, THH, and all these kind of things. So the key feature here is that you send Karubi sequences to co-fiber sequences, because you're supposed to think of Karubi sequences as like somehow exact sequences in the world of stable categories. So that's a definition that you can make. Here's another definition that you can make. A map A to B inside cat-perf G is said to be a motivic equivalence if it is sent to equivalences by any G localizing invariant. And we'll call the collection of such map, I don't know, W underline mod, let's say. So yeah, here that's like a slew of definition. If you've never seen this before, it's a bit confusing. But let me just recap what has happened. I had to tell you what a Karubi sequence is in order to be able to define for you what a G localizing invariant is. And I need to define G localizing invariance for you in order to be able to declare what motivic equivalence is. So that's roughly how this thing goes. But yeah, now, but yeah, by the way, this is the style of definition that's given by Ramsey, Sosnovingas. And again, just following them, you can define mod log underline to be cat perf underline, and then I invert these motivic equivalences. That's it. Like this is the definition of mod log. And so this is exactly the same as what was done by Ramsey Sosnovingas, except for the fact that when I define G localizing invariant, I had to require this extra thing, but that's about it. Everything else is more or less the same. So that's a definition that you can make. And now comes a theorem. So the theorem has some statements, so I'll go through them one by one. The first thing is that this mod log is G presentable and G stable. This is kind of not hard once you are given this paper of Ramsey Sosnovigas. I'm not going to talk about this. This is something you can do. The localization witnesses the target as the universal G localizing invariant. Again, just copying their proof, this is really not hard. You just do exactly as they did. What this says is that kind of if I have a localizing invariant, let's say E from cat perf to some E, then I'm going to admit a unique map from mod log to E. That's what it says. In particular, this actually you can use this to also obtain the universal property that was kind of articulated by Blumberg-Gapner-Tabuada. So this is G localizing invariant in whatever sense that is sane to talk about. And here's the last point, and this is sort of the key thing that I want to talk about for the rest of this talk, is that the functor U refines to a G-symmetric monoidal functor. And this is actually kind of tricky. Anyway, we'll come to that, but before that, let me just quickly say what's the corollary. The corollary is that equivariant K-theory refines to a G-leg-symmetric monoidal functor, because you can show that also as in the non-equivariant context, K-theory is co-represented by the tensor unit in mod log. So, because the functor U is G-symmetric monoidal, and because mapping from the tensor unit is G-leg symmetric monoidal, this whole composite is G-leg symmetric monoidal. And here by K-theory, I mean that you can also show that this whole composite is actually equivalent to the inclusion of cat-perf into Mackey functors on cat-perf, and then I apply K-theory to land in Mackey functors and spectra. So the K-theory that you think that you thought to define is this one, and I'm saying that this has a G-leg symmetric monoidal functor, a G-leg symmetric monoidal refinement when you restrict it to cat-perf. Why this is important is that in particular it says that it sends stable categories with norms to ring G spectra with norms. And this is somehow the key point. And this last result, this consequence, has been achieved to various degrees in the literature. So I should say that this result about localizing motifs, you can use it to deduce that also connective algebraic K theory takes norm categories to norm ring spectra. So yeah, this surprisingly, this localizing motifs version implies also like the additive motifs or splitting motifs. And this statement for connective algebraic K theory has been done by Knossen, Hausen, Lange, and Linsken. So they showed that G commutative algebras on Ket-Perf get sent to G commutative algebras on spectra. They use the theory of bispans and so on. And in my thesis, I also showed that connective algebraic K theory assembles to a G-like symmetric monoidal functor when the group is of order power of 2. It is a bit technical because I couldn't really deal with the cubes properly last time, but these are some things that has happened in literature. But I just want to say that this result it recovers these results by Knossen, Hauser-Lenz, and Linsken, but it's stronger because it says that I can now not just talk about G commutative algebras. For example, if you're lucky in life, you might find EV algebras inside Ket-Perf for EV for V some representation. So there's this thing called EV operas, and you might find EV algebras on Ket-Perf. What this result implies is that the K theory of EV algebras is going to give rise to an EV algebra in spectra. So at this level somehow you get a lot of other structures. But yeah, so that's the consequence. Now I want to tell you why this is a tricky thing to prove. By the way, does the statement make sense? Okay. Um, what's the key problem to solve? The key problem is the following. So non-equivalently, this is such a non-problem that yeah, you don't even realize that it was a thing that you had to do because it was so easy then. And the thing that you have to show is the following. To show that U is symmetric monoidal, you need to say that if A to B and C to D are motivic equivalences, then A tensor C to B tensor D is still a motivic equivalence. This is something you have to show. It's just a standard thing about Dweikern localizations. If I have a Dweikern localization, if I invert some maps, to show that this inversion is compatible with symmetric monoidal structure, this is the statement that I have to show. And this is easy there because you can curry, meaning to say I can factor this map into this composite, right? I can kind of keep A fixed and vary C to D, or I can keep D fixed and vary A to B. And now because tensoring with a fixed object preserves Karoubi sequences, this is easy. You can very quickly deduce that this map is a motivic equivalent. And similarly, you can deduce that this map is a motivic equivalence, and so this interested to study, you can factor it as a composite of two motivic equivalences. And so in particular, this map is a motivic equivalence. So yeah, again, it's so easy that you just kind of overlook that you have equivariant tensors in this way. You see, because like when you tensor things equivalently together, the group symmetrizes all the tensor factors. So you cannot like separate them out without breaking the symmetry. More concretely, what this is saying is that if I replace A tensor C here with tensor GA and here with tensor GB, I can make this factorization, but these maps are not going to be G equivariant anymore. So I cannot factor the map that I'm interested in as motivic equivalences in the world of G categories. Even though I can do it underlying, if I just forget all the G action, I cannot nonetheless do it like for taking care of the G action also. So yeah, you just can't do this. And so it is a very kind of non-linear difficult thing, but the technique will then be to say that I can use isotropy separation to somehow linearize all the equivariant non-linearity. That is going to be the slogan going forward. So yeah, I hope I've sort of explained in an understandable way, like what why there's still something to do, kind of like why this is not as trivial. So yeah, now I want to just give a feeling for how the proof works. Um, right. So let me um, highlight this technique of isotropy separation at the categorical level. So in joint work with Dominic Kirschner and Christian Kramer about equivariant Poincare duality, yeah, we introduced this kind of categorical isotropy separation, which says the following thing. Suppose I have a G presentable stable category C. I can smash it with the co-fiber sequence involving this universal spaces, and I will get this solid co-fiber sequence on top. So this J lower streak phi G functor. This is such an important construction. I'm going to give it a name. I'm going to call it phi G of C. Okay, and if you know these words, in fact, um, this system extends to a stable Récollmont. So, what it means is just that J lower streak admits a right adjoint J upper star, and this admits a further right adjoint called J lower star. And similarly, phi G admits a right adjoint, which admits a further right adjoint. Anyway, here's the thing you can get. And here are three important facts about this construction. The first is that phi G of C is actually an ordinary presentable stable category in the following sense. So remember, G presentable categories in particular consist of the data of presentable categories for every subgroup. Phi G of C has such a data, but what's important about this is that all this data is concentrated at level G. So this is a G category which looks like something at level G, and it's just given by 0 downstairs. So it is really essentially just a presentable stable category in the usual sense. So somehow in the sequence, you see you've isolated kind of the difficulties about C into all things concentrated in kind of smaller subgroups, and one part which is concentrated in the top group, but this is now a non-equivariant problem. Another thing that's important is that phi G and J upper star are jointly conservative. I mean, this is just a standard fact about stable Récollmont. But what this means is that if I want to check an object in C is 0, or if I want to check that the morphism in C is an equivalence, I can check it by pushing it via J upper star into here, and pushing it via phi G into here, and check that the object is 0 in these two worlds. And last, this phi G is very useful because it allows you to trade a complicated equivariant colimit into an ordinary colimit. And what it says is that if I apply phi G to a colimit index over some G category, which is complicated because it's actually not given by level-wise taking colimits. It's much more complicated than that. Phi G nonetheless goes through this colimit and turns it into an ordinary colimit index over the fixed point of the indexing category. So now again, I've used phi G to turn difficult abstract things into something in ordinary category land, which you can deal with. So using these things, we prove as a key tool in this localizing motifs paper that that you have the following characterization of fully faithful maps inside cat-perf G. So suppose I have a functor from C to D, then I can check that it is fully faithful by checking that when I restrict to all the proper subgroups, it is fully faithful. And when I apply phi G to it, this is now a functor of ordinary stable categories, that this is fully faithful in the ordinary sense. Yeah, so here I guess I should mention that you can also do this isotropy separation at the level of small G stable categories, and this is what this symbol means. Yeah, so you might be wondering like why did I suddenly talk about fully faithfulness? We'll see this in just a bit, but just to look ahead, the reason here is that this is going to allow us to check that a sequence in cat-perf G is a Karoubi sequence. Because remember when I said it's not a Karoubi sequence is a fiber co-fiber sequence. In particular, as a necessary condition, you need that the first map is fully faithful. And we'll come to such examples later, but this is why this is going to be important. Okay, so that is kind of the tool. Now I want to actually sketch the proof of this result um about the map U from cat-perf to modlog being G symmetric monoidal. Um, you just by unwinding the theory of Dweck-Kahn localizations, this is you're reduced to showing the following thing. So remember I said cat-perf has got multiplicative norms. In particular, it has these non-linear functors uh, from H stable categories to G stable categories, which you should think of as kind of taking a stable category with a H action and tensoring it over G mod H. So now there's a G action kind of commuting the different factors. And we see this thing that you need to show. And you can kind of easily reformulate this to say that this is the thing that you need to show. So norms goes from cat-perf H to cat-perf G. The functor U goes from cat-perf G to modlog. I need to show that this composite sends motivic equivalences to equivalences. Yeah, this is just a simple reformulation of this thing that we need to check, but this is a statement that I want to focus on now. Right, so okay, this is a thing that you have to check, and so let A to B be a motivic equivalence in cat-perf H. Consider the following map of co-fiber sequences. So I can apply U norm of A, and then I smash it with the isotropy separation sequence to get a co-fiber sequence on top, and similarly I can get a co-fiber sequence below. Now, because it is a map of co-fiber sequences, to check that this middle map is an equivalence, it suffices to check that both these outer maps are equivalences. And here, the slogan to chant is just that this left map is an equivalence by induction. Okay, I'm not going to spell out the details, but essentially because EP plus kind of only sees the information coming from proper subgroups, you can just say, oh, this by induction on the size of the group, this map is known to be an equivalence. The base case being, the case of trivial groups where everything that you ever want to know is known. So whatever, this thing is an equivalent. So you see, to show that this is an equivalence, it is the same as showing that this map here is an equivalence. It's phi G U of norm of A. Okay. So yeah, this is what we want to focus on now. And the main claim now is that this functor, so remember U of norm goes from cat-perf H to mod log, and then I can further compose with phi G to land in phi G of mod log. This is whatever, this is some category which is unknown, but I think it is interesting to kind of study, but okay, it's something abstract, but nonetheless, this is a norm, it is an ordinary category. So remember, because this phi G turns any kind of G presentable thing into an ordinary presentable thing. Anyway, the main claim here is to show that this functor sends Karoubi sequences to co-fiber sequences. Once you've shown this, then you would be done, because once you know this property, you know that this whole functor is a localizing invariant. And because it's a localizing invariant, it's going to send motivic equivalences to equivalences, which will imply that this map is an equivalence. So that's how the logic goes. Okay, so that's what we want to focus on now. So suppose A to B to C is a Karoubi sequence in cat-perf H. Remember, in particular, this means that this functor here is fully faithful. Now you can do the following thing. You can apply norm to this co-fiber sequence, and you get a complicated co-fiber sequence, which looks like this. I will give an intuition for what this thing is. So the general statement that you will have seen in your life is that tensoring things does not, sorry, tensoring two co-fiber sequences don't give you another co-fiber sequence in the naive sense. Uh, but you can nonetheless get a co-fiber sequence, kind of like the fiber term. So here, let me give you an intuition for this. This is going to be a useful and instructive one if you have never seen this kind of thing before. So imagine you're in the case of G being the group C2. If you have a co-fiber sequence A to B to C, you can tensor everything together and you get some big diagram. In particular, you get this square. So A tensor A tensor B, B tensor A, B tensor B. All of these map to C tensor. This diagonal term. But, even so, you still have a co-fiber sequence. If you replace this last term here, you replace A tensor A by this big push out here, which is what this whole thing is. This is nonetheless still a co-fiber sequence. This just comes from the fact that, tensor preserves kind of co-limits in both variables. But anyways, this is a general fact. And here, I've drawn these dashed lines to indicate, to remind you that actually in this equivariant situation, things are even more complicated because this is not an ordinary push-out, but this is rather a C2 push-out, where the group C2 is acting on this whole diagram itself by swapping this vector and this vector. And so kind of in the case when G is C2, this is actually not just your everyday push-out. This is a push-out indexed by the diagram, kind of the C2 span, where you can imagine the span, but then, with the C2 swapping the two legs. And, this is the group C2, and you can imagine when for other groups you have, some co-limit indexed by some more complicated equivariant cube. So this is where this equivariant cube business shows up. It shows up very naturally because when you study K-theory, it is after all about Karoubi sequences. And to study how this interacts with the norms, like these cubes will invariantly show up. So this is why they're important. And this is why you need the language of G categories in order to be able to even like speak about them. So this is somehow the co-limit indexed by the punctured equivariant cube. So you can imagine the cube of size G mod H with the group G acting by permuting all the coordinates, and then I just puncture away from the final object. Anyway, so here's a co-fiber sequence, which is good, but it's still very scary. Now the claim is that this co-fiber sequence is in fact a Karoubi sequence. This is the first thing you need to show. And in order to show that, it suffices to show that this map alpha is fully faithful. So I hope all the sort of different ingredients and different aspects I've talked about are starting to come together. This is why I had to introduce all this tool about checking fully faithfulness, is precisely to kind of check that some sequence you have is a Karoubi sequence. And to check that, it suffices to check that the first map is fully faithful. So in order to do this, I apply the tool and I say that, okay, by induction on smaller subgroups, everything is known up to applying phi g. Now I want to apply phi g to this big term, and applying it there. And remember, phi g can walk past equivalent co-limits by turning it into an ordinary co-limit. And because these equivariant cubes, you can just think about it in your head that somehow the fixed points are only the initial and final objects in the cube. So because I've punctured away from the final object, when I take the co-limit of the fixed point, it is just going to be, um, evaluating the diagram at the initial object, which is given by phi g or norm of A. So just to recap, I want to apply this key tool to show that alpha is fully faithful. By induction, it suffices to apply phi g both sides. I can analyze what phi g does to this thing by this maneuver. And so upon applying this isotropy separation, I get a map from phi g norm of A to phi g norm of B. And by a separate argument about norms, you can show that norms actually preserve fully faithful functors. And so because A to B was fully faithful, norm of A to norm of B is also fully faithful. And therefore phi g of norm of A to phi g norm of B is also fully faithful. So all in all, I've argued, kind of sketched out for you how you can show that this map alpha is fully faithful. Why this is good is because it is now a Karubi sequence. And so U is going to think that it's a co-fiber sequence inside mod log. So here's a conclusion that you get now. The norm sequence, now this is now a co-fiber sequence in mod log after I apply U. So this is good, but we are not done yet because we still have this weird complicated term. And I want to now explain to you how to get rid of it. You can do a kind of Davisage argument by filtering the size of the cube to see that phi g, this thing is difficult. I mean, there's no way around it. It's just a complicated term. But nonetheless, what I'm saying is that once I apply phi g to it, it becomes simple. Namely, it just becomes phi g of u of norm of A. And yeah, I don't want to spend too much time on this, but essentially the point is that I can filter the cube by somehow the size of the subsets. And I can compare the co-limits taken over, this different levels. So I feel, co-limit of those things up to size I maps to those things of size up to I plus 1. And the key point here is that you can use this key tool to show that this map is fully faithful and that the co-fiber is a properly induced term, meaning the co-fiber of this map is going to be some stuff which is kind of induced from all the smaller subgroups. And therefore, once you apply phi g to it, you're going to kill off these induced things, and phi g is going to think that this map is an equivalence. So yeah, this is roughly what I explained. So all in all, what I've shown is that this is a complicated co-fiber sequence still, but upon applying phi g, I get this co-fiber sequence. This completes the proof because this is what I wanted to show. I claim that phi g u of norm is it takes Karubi sequences or co-fiber sequences. So this is what I've done. So that completes the proof. So you see, kind of the slogan here is that you somehow, if you want to deal with this nonlinear stuff on K theory, this power operation type things, you will have to deal with some cubes at some point, and these are rather tricky, but nonetheless, you can kind of filter the problem away by kind of skimming off the last thing that you have to show, the inductive step, and this part that you've skimmed off turns out to be a rather linear and non-equivariant problem. This is sort of essentially what has happened. So yeah, that's sort of the sketch proof. And last, just to end the talk, I want to bring up two sort of applications of this whole theory. So first is this equivariant trace map. Let me quickly say that you can define equivariant THH, but again, like if you apply this Mackey functor style thing, it just doesn't quite do the correct thing because it's going to think that G spectra is not the equivariant sphere. Okay, and this is an important philosophical point because THH is a symmetric monoidal functor from cat perf to spectra. So it's supposed to take spectra to the sphere spectrum in particular, but this is just not the case. Nonetheless, there is a natural replacement that you can do, and this is that you can use this theory of traces by Oiwa, Shorotsky, Sibilla to define somehow the correct version of equivariant THH. So unlike K theory, this is not pointwise THH. It is somehow doing trace theory internal to G categories. It turns out that by doing this construction, this is a G-symmetric monoidal functor, which in particular means that it sends G spectra to the sphere spectrum, but also that it preserves norms. So it's important. Anyway, because this is a G-symmetric monoidal functor, which turns out is also a localizing invariant, you can use the universal property of K-theory that we've established to get an equivariant trace map from K to THH, which is compatible with the norm. So this is a transformation of functors from Cat-Burf to spectra, which is a transformation of G-lexsymmetric monoidal functors. What this is saying is that if I have, let's say, a ring G spectrum with norms, then applying this trace map to it is going to give me a map of ring G spectra with norms. So we don't exactly have any applications for this, but I think this should be an important sort of basic um uh basic sort of result for the general theory of equivariant K theory. This should be interesting. And the last quick thing that I want to say is just this fun thing that you can prove with this setup. Um, so long story short, you can show that every genuine G spectrum is the K theory of some G stable category. And here, this all these words is just to say that you actually cannot deduce this directly from the Ramsey or Vinger's work. Essentially because they constructed a section to the K theory functor, but the section does not preserve products. So you cannot just hit Mackey functors on both sides to say that, this section induces a section at the level of Mackey functors. But anyway, all of this just to say that using this notion of equivalent localizing motives that we defined here, you can nonetheless prove this result. And this uses the fact that the map U from Cat-Perf G to mod log G is essentially surjective because it's a Dweikant localization, and it uses the equivalent trace map that I just defined just now. This will allow you to prove such a thing. So this is saying that in fact all genuine G spectra, they are not just K theory of some object in Mackey functors, but they're even K theory of some kind of categorically natural object, which I call Cat-Perf G. Yeah, so anyway, I think time is up, so yeah, let me stop there.
You. Are there any questions?
Yeah, here is a question from the audience in the room.
Uh-huh.
So we have some presentable G category theory. Do we have some analogs of Efimov's dualizable G category, or maybe something like
Yeah, yeah.
do we know the G equivariant motivic not localizing motivic category is somehow is rigid, or maybe some G dualizable things like
I think so. So yeah, I've discussed this with Maxime and Thomas, and we're convinced that yeah, you can use Efimov's thing about rigidity of motives to also deduce that mod log G is somehow rigid. But yeah, we haven't written that down.
okay. Thank you.
Yeah, yeah.
I have a question.
Yes.
Is there a comparison of the mod log G that you defined to those naive ones that you introduced at the beginning, like from BG to mod log, for example?
Yes. So actually, yeah, you can use this um to. So I think the statement is that you can also define equivalent motives for functors from BG to Cat-Perf. And as I said, this is not functors from BG to modlog, but I think this is nonetheless still a Dweikant localization of the thing of this equivalent modlog. So yeah, it is somehow just a further localization of this thing that I said. Yeah.
Mm.
But still, even so, like this modlog is already kind of also enough to say that uh it says it implies the following thing, namely if I have symmetric monoidal stable category equipped with the symmetric monoidal G action, and I take various homotopy fixed points, the K theory of this is also going to have norms. So yeah, those are some various things you can talk about this Borel type theories. Yeah.
Let me